So the next speaker is Aina, Linn, who will tell us about the Nextgen modality.
Thank you so much. So thank you, everyone. Yeah, I'm Aina, so I'm going to present our work today on the Nextgen modality, a modality for non-frame preserving updates in separation logic. This has been joint work with Friis, Vindum, and Lars Birkedal. So in general, I think we can all agree that the frame rule and frame preserving updates are very central to separation logic. So if we consider the very classic core triple for store operation, we can do this update because we have exclusive ownership, so that's what the points to predicate means, over some location L. And what this means is that it's always safe to apply the frame rule that we all love. And in general, the frame rule and frame preserving updates are very suitable to express any kind of local change to the physical state. Right, so here we're only updating L, which is why it's frame preserving. However, in general, not all changes are actually local. Right, so sometimes we will have certain setups that lead to global sweeping changes of the physical state. So some examples include machine crashes, in particular in the presence of durable memory. This might deallocate a bunch of memory. It can also include garbage collection, which also deallocates a bunch of points to predicates. And finally, another example include the frame deallocation if you have a language with a call stack. And none of these updates are necessarily frame preserving, right? Because they're making these sweeping global changes to the machine state. So to see why this is an issue, I want to look into more detail of this third example. So let's imagine we have a language with a call stack. Here we have an expression, return 2. And what this means is that we're going to return 2 frames down to frame k. So essentially, this instruction is going to deallocate frame at I and j. All right, so let's try to describe a triple for this. Maybe a first, well, quite naive attempt is to say, well, since this instruction executes in the topmost frame, naturally, they might own the points to predicate or the resource of the topmost frame. Okay, so we can imagine that the rule looks like this, where essentially the frame gets deallocated and consumed by return. But of course, this is not sound. Right, so we can apply the frame rule with j, but since j also gets deallocated, this doesn't work. And the only way around this, in this case, is that we must describe a rule that contains all of the deallocated stack frames in the precondition. The precondition must have all of the resources that we're actually deallocating. And while this rule is sound, it's maybe not entirely satisfactory. It means you always need to carry these frames around for all calls in case they return to a lower frame. So it's not like as modular as we might want it to. And this gets even worse in some of the other examples. So for example, if you have crashes, then you essentially need to put all of the resources that might get cut by a crash somewhere in your logic. I mean, you can't just carry them around all the time. It gets really difficult. Okay. So in this work, we're going to present an alternative solution with non-frame preserving updates. So more concretely, the main contribution of this work is the basic Nextgen modality. It's written here with the squig, and I will explain later what the T means. But essentially, this modality will define some kind of, or will express some kind of global event. So if we look at our return program from before, our goal is to be able to describe a triple that now simply marks the continuing program C with this global event. So note here, we don't need to carry around the resources that we are deallocating. Instead, we're going to put this global event, which here is a pop, before the rest of the program. Now we are defining the Nextgen modality in Iris. So I'll give very brief background into Iris. I will especially mention this third part because this is important for the definition. So what is Iris? It's a higher order concurrent separation logic framework. It comes equipped with a bunch of modalities, so namely later modality, which means a predicate holds after one step, so that's the triangle. The always modality means something holds at every step or always, and the frame preserving update modality, among others. Next, it also comes with iris invariance. So that's written with this box. That means that the assertion I holds at every step of execution. And finally, a big draw of iris is that it comes with user-defined resource algebras or user-defined ghost state. And what this means is that users of iris can define any kind of resource they want by defining a resource algebra, so here written as MI, and add it to the collection of resource algebras that you work with. So in general, we're going to write the ownership of some resource A, which is part of some resource algebra MI, with the dashed box. Right. So let me get into the technical details of the basic Nextgen modality. How is it defined? So let T be some transformation of a resource algebra MI. Then the easiest way to see how we define the basic Nextgen modality is to look at the introduction rule, which looks like this. Right, if we have a resource A, where A here happens to be the resource algebra MI, then when we introduce the Nextgen modality with transformation T, we just apply T to A. Now note, this modality is not frame preserving. Right? So in particular, this statement does not hold. And that's because T might actually have an effect on the resources below it, right? So if Q has some resource A in it, then we cannot just freely put it under the modality, because T might transform it. Okay. Now the definition is quite simple. This is it. So let's look at some of its properties. Right, so first of all, we've already seen the introduction rule. Also, this modality is monotone. So that's the second statement. And thirdly, we can compose these transformations together. Next, it also behaves quite well with the existing iris modalities. Okay, so it commutes with later, and it also commutes with always under some condition that I'll not get into the details of, but it is very sensible. Okay. And at this point, I want to take a small sidebar and give a small comparison to what is perhaps one of the most related works currently, namely perennial. So what is perennial? It is a framework for verifying concurrent crash-safe systems. Okay, so this falls under one of these examples I mentioned earlier with crashes. And indeed, they also define a post-crash modality, it's written with this diamond, to express the way in which resources change due to a system crash. This work is also done in the iris framework. Now, unfortunately, the post-crash modality has a couple of limitations. So firstly, it doesn't commute with the box modality. And also, it doesn't have interaction, very well-defined interaction with custom ghost state. And I mention these limitations because the basic Nextgen modality solves these, essentially. Okay, it has very well-defined interaction with custom ghost state. And it also commutes with the box modality. So that's it for the most basic version of the Nextgen modality. But I mentioned how one of the draws of iris is that users can keep defining new resource algebras. And in fact, it means that in practice, you don't just have one resource algebra, you have a collection of them. So what does that mean for our Nextgen modality? Let's say, well, we have a collection of resource algebras. In iris, it's usually defined like this. You have a product of n different resource algebras. And for each of these, you will have multiple instantiations of the same resource algebra. Okay, so this map is to define multiple instantiations of MI, each parameterized by a ghost named gamma. And we're going to essentially do the same for the Nextgen modality. Okay, so we're going to maintain this product, again with a map parameterized by gname. These will essentially align. And for each of them, we might define a transformation. So in fact, our introduction rules look like this. If we happen to have a gamma that is within this map or transformations, then we look it up and apply it. If gamma happens not to be in the map, then the introduction rule does nothing. Okay. Now this has been quite abstract. So let's go back to our case study from the beginning, the call stack deallocation, and see how to actually define a usable Nextgen modality. So to recall our goal, we want a rule that looks somewhat like this, with this global event that marks a pop event. And really, the game here is to define the right transformation T that will define this event. We introduce the language that we're working with for this case study. It's called stacklang. The operational semantics is a fairly standard lambda calculus with continuations, except it also has a high-level representation of a call stack, S. S here is a list of frames. Each frame is a small map, and the topmost frame is to the left. Now, frames are pushed upon function calls. So if we have a function call here, we're going to push an empty frame to the head, and they're popped upon function returns. So in the simple case, if we just return one step down, we're going to remove f here, which is the topmost frame. However, I mentioned that we have these continuations that let us skip frames. So more generally, what does a return look like? It is an invocation of a continuation, written like this, that targets the ith frame from the top and continues the continuing program k. Now, k here is an evaluation context that takes v to continue. So v is the return value. And this instruction now pops the I topmost frames. Okay, so we're cutting multiple frames at once. Now, the first step for defining our program logic is going to be defining the ghost state we work with. There's three main ones, so three different resource algebras. One for heap locations. This is standard points to predicate. Next, we have one for stack locations. They're additionally going to have this k, which indicates which frame they belong to. And finally, we're going to have a resource algebra to write to express the size of the stack. So the symbol here at the bottom left means the stack has m frames. Okay, let's look at an example rule. So first, we start off a bit simple. Stack allocation. So stack allocation needs to have at least one frame in the stack. So we assume that we have the resource that expresses the size of the stack being m. M must be non-zero. And in the post condition, we get a fresh points to predicate of a new stack location in frame m-1. Now, more interestingly, is the rule for return, or the invocation of a continuation. Okay, so since we are returning to I frames from the top, we need to know that there are at least that many frames to pop from our stack. So we assume that the size of the stack is m+1. And in the continuing program, we have a stack size of m in our continuation. And importantly, we need to mark this event to say that we're deallocating stack frames. All right. OK, so we've now gone to the fun bit, is to define the actual transformation. So we want the transformation to simply remove frames from our stack S. And we're going to define it as scut. Of course, we're defining many next-gen modalities here because we want one for each possible number of frames we're cutting. So scut n takes the n as a threshold now, and will remove every stack frame above it. Okay. We can now define the modality that we're going to use in the program logic. It's written with this n as a parameter. And essentially, we're going to look up I, which is the index of the stack resource algebra, and we're going to insert scut n at that location. Okay. Let's look at some properties. Right, so first, since this is really only about the stack resource algebra, we can just introduce it in front of the heap resource algebra without any effect. Next, if the stack location is below the threshold, right, so if we are cutting all frames from n and above, if the k, which is the frame of our points to predicate, is below, then nothing happens. However, if it's above, it gets consumed. Okay, so in this case, the introduction rule essentially consumes the points to predicate. This means it gets deallocated. So what is the rule going to look like? Finally, we simply say that since we mark the event as cutting all frames above m, then we have next-gen m in front of the rest of our program. All right, so this is our rule. Let's use it in an example. Now, I hope it's large enough to read. I wanted to go through the whole example really to highlight this point that we don't need points to predicates for the frames that we're deallocating, and why that's nice. Because we have a program here. Okay, I cannot use my mouse. It is a function application of a function that returns to frame n from the top. And locally what it does, it's going to allocate a new stack location. Then it's going to do some computation over it, and importantly, it's going to read from this global G before it returns. Right. Now, the only assumption we want to know is what happens to the continuing program K. And here, K only needs to know that the stack size is M, if it starts out at M plus N, and that G still exists. Okay, so our assumption is that given the stack size M and G points to 1, we can continue the program K. All right, so we do a function call. That means we are pushing a new frame onto the stack, so the stack size grows by 1. Note here that our continuation shifts because we are now targeting the n plus 1th frame from the top. Next, we allocate this new local stack location at frame m plus n. We then do a substitution. Okay, so that's fairly standard. And next, we do the actual computation. So I've skipped some steps here, but essentially we load from L and from G, and then add up the results together, which gives 43. And we've now reached the important and fun part of the program, which is the return. So we apply the return rule, which gives us this triple. Now here, I'm cheating a little because I'm using Hoare triples instead of weakest preconditions. But this is essentially meaning that we want to, in order to introduce this Nextgen modality, we're going to need to introduce it in front of all the relevant resources in the precondition. Right, so in practice, in the iris proof mode, you end up with this obligation. Right. And here in the first case, well, this modality doesn't affect the stack size, so this is introduced very easily. Same for the heap. But for the stack resource algebra, right, since this threshold is above M, this whole location gets deallocated. Okay, but luckily, we didn't need this resource for our assumption, so we just continue. Okay, and we can use our assumption. However, what's really nice here is that our spec for this function doesn't need to mention anything about the frames of m plus 1 all the way to m plus n. Okay, so it's very local. Okay. So let me give 2 final remarks. Right, the first one, I really emphasized how nice this was, but what do we lose? And it's quite severe, because we do lose the frame rule, at least in this way, that we integrate the Nextgen modality with the program logic. And to see that, we can see this with this counterexample. So let's say we return and pop the whole stack with our return statement. Then, of course, we can't apply a frame rule using any stack location. That would be unsound. Right, so we do need to lose the frame rule, but this seems overall much too restrictive, especially because we have all these resources that are independent from stack locations. Okay, so we do set up a way to recover the frame rule. In particular, resources that are independent of the possible Nextgen modalities should be able to be framed away. And in order to express this, we introduce an independence modality. It's defined on top of the basic Nextgen. It expresses that some assertion P is unaffected by Nextgen modality N. And our frame rule can then look as follows. Right? So if we have a frame R which is completely independent of any possible Nextgen event that would happen, then we can apply the frame rule on it. The second remark I wanted to say is another big plus of the Nextgen modality is how well it behaves with the existing iris infrastructure. Right, so I already mentioned that it behaved well with existing modalities. There's also some very interesting non-trivial interaction with invariants. So iris invariants are implemented using resource algebras. So it is completely possible to define a transformation for that resource algebra for the environs. And that means that we can now define a new type of invariant that allows us to contain resources that might actually be deallocated or affected by transformations. So in the paper, we introduce such a variant of iris invariants, which support non-trivial interaction with the Nextgen modality. Just to give a bit of flavor, we have an invariant that is annotated with a threshold n, and this essentially describes the lifetime of the invariant. So if k is below that threshold, then we can put an the k points to predicate within this invariant. Now this is just for the stack line, but we also define this in a sort of language independent way, same for the invariants. And you can play around with it yourselves. All right, so in conclusion, we have extended the iris-based logic with a new modality for non-frame preserving updates. We've integrated the new modality in a program logic for a language with non-local updates as a case study, where we show how to recover a version of the frame rule. And also we show how we can support non-trivial interaction with iris invariants. Now all of this is mechanized in Iris Rock, and it should be available online. Thanks.
Thanks for the talk. So in your last slide about the frame rule, how do you reason, how do you prove that your a concrete predicate is independent? Is it easy?
Okay, that's a good question. So we have set up a bit of help for that. Like there's some similar to the iris proof that can allow you to do this. But essentially, you need to show that you can introduce the next-gen modality in front of it. So the proof obligation is that what happens when I introduce it, is it the same afterwards? With the support of the iris proof mode, it does become rather seamless. So if you've set it up properly, then you just get your instances of the type class, and this happens freely. And in fact, it's also integrated with the frame rule. So you can do an iframe, and it figures it out itself.